Hello everyone, I'm Vinh. I'm from KAIST, Korea. Today I will present our research topic. It's titled about sensor fusion by spatial encoding for autonomous driving. Nowadays in autonomous driving, multimodal perception methods that fuse the data from camera and LiDAR have made significant advancement in the field of autonomous driving. Although the LiDAR is excellent at understanding the geometric properties of 3D scenes, its limited ability to detect semantic objects such as traffic lights make it difficult to be used in practice. In contrast, camera provides semantic information, but they do not have a 3D depth perception. Therefore, integrating camera and LiDAR while making up each other weakness is crucial in autonomous driving nowadays. Let me introduce some related work in this area. Based on when the different sensors are fused, the current methods for multi-sensor fusion can be classified into three categories. The first one, the detection level fusion, is the most straightforward approach. This model generates bird's-eye view detection for each sensor and aggregates and deduplicate them. This approach does not fully utilize the unique characteristics provided by each sensor. And the second method is the point level fusion combines data from LiDAR point cloud with the feature extracted from camera images. This involves enhancing LiDAR point with camera pixel, but camera to LiDAR projection can result in semantic loss due to sparsity of LiDAR point. And for the proposal level fusion, the notable works now they propose initial bounding box using LiDAR feature and refining them iteratively using camera feature, but resulting in a weak representation of local and global context. So our research addresses these critical gaps, hinting at the comprehensive nature of our proposed solution. Here's our architecture model. The proposed method shown in this figure comprises three main processes. The first step is about extraction the spatial features from all modalities individually using CNN. And the second one is about integration of a set of encoding to generate the interpretable features. And the last step, we predict the forward waypoints utilizing the previous interpretable feature. So let me delve more detail about each step. The first step, integration, the extraction of spatial feature. The camera images and LiDAR point clouds are inputted into two parallel backbone networks such as RegNet. This process generates different feature masks for next step. And the most important step in our approach is the integration of this feature. The feature mask from each sensor is processed using one by one convolution to obtain a lower channel feature map, resulting in the list of tokens. And the fixed 2D sinusoidal positional encoding is added to each token to preserve positional information. We call that the local information. Additionally, learnable sensor encoding is included to differentiate the tokens from different sensors. We call that global information. And finally, the encoded tokens from all sensors are concatenated and passed through the transformer decoder. And each decoder layers utilizing the queries to gather spatial information from multimodal feature through the attention mechanism. And finally, the compact representation of the environment is encoded in a 512-dimensional fused vector. And for the first step, the transformer decoder is accompanied by a prediction module to forecast the weight points. Weight points, it means it represents the specific positions and orientation on the road network and are crucial for various tasks in autonomous driving, such as path planning and vehicle control. Here, the 512-dimensional fused vector is passed through the multi-layer perceptron MLB to reduce the dimensionality to 64, and the resulting vector is fed into GRU, gated recurrent unit network to predict the weight point. Finally, our network is trained using an L1 loss, which measures the discrepancies between the predicted and ground truth weight point. And for the experiment, let me introduce some details about the implementation. First, about the training dataset, we use the color simulator. Color simulator is used to train and test autonomous driving model nowadays with a large dataset of images and point cloud. In this research, we use two challenging benchmarks. Our method is evaluated with the Longest6 benchmark and Town05 Long benchmark. It's really common in that field, in this field. The Longest6 benchmark comprises challenging driving conditions with a high dynamic agent density, combined 6 weather and 6 daylight conditions. And the Town05 Long benchmark, it encompasses diverse road types such as multi-lane roads, single-lane road, bridges or highway or exist. The proposed method is evaluated using 3 main metrics: route completion, infraction score, and driving score. We also show the additional metrics. For example, the collision with pedestrian, the collision with the vehicle, and so on and so forth. Here the results are in 2 benchmarks. 2 tables show the result of our method and some state-of-the-art approaches in this area. Let me introduce briefly about other methods. The TransFuser is the modality integration technique, but excluding local and global embedding. The latent TransFuser adopts a similar architecture to the TransFuser, but substitute the bird's eye view LiDAR with the fixed positional encoding image. The late fusion independently extract image and point cloud features, then fuse them via element-wise summation. The geometry fusion combines LiDAR and camera through the multi-scale feature fusion using projection. As we can see in the table 1, our proposed method outperforms other model with the Longest6 benchmark in 2 major metrics, with the highest driving score of 45.64 and highest infraction score of 0.65. With the Town05 Long benchmarks, the results presented in the table 2 indicate the superior performance of proposed method with the top infraction score. And for discussion, other methods, they prioritize reaching the goal at all costs that make make more mistakes and violate the traffic rule, result in the lower infraction score. But our method take into account the surrounding environment and make more correct decision, which enhances the safety of driving process. To sum up, sensor fusion is critical for perception system for the task in autonomous driving and robotics also. This work introduced the novel multimodal fusion transformer that effectively capture the overall 3D scenes context, integrating local and global context. Compared to the shorter techniques, the proposed method achieves improvement in driving score for two challenging benchmarks. That's all for my presentation.